again, welcome to our online seminar today about modeling and predicting adsorption processes in porous media. My name is Tabea Sterbak, and that's what we're going to look at today. Why are we here to talk about adsorption? In the filtration industry, adsorption-based processes to remove contaminants and odors are present in a wide variety of applications in daily life. With GeoDict, you can get more insights into your dynamics. So you can use GeoDict to do digital prototype development, to cut material usage, to reduce testing time, but also get deeper product knowledge. So what are we going to learn today? We look at the generation of a cabin air filter with 2 fiber layers and an active carbon layer. We also gonna look at the adsorption simulation, so we're gonna check what data you need to start such a simulation. We're gonna look at the setup, and then we're also gonna look at visualization and the results afterwards. In most of the applications, materials with large internal submicron surfaces like activated carbon or zeolites are used. For example, in agriculture, these filters protect farmers against fertilizers and pesticides, whereas our drinking water or wastewater also benefits from these materials. Cabin air filters and devices for personal protection protect human lives from gases like NOx or SOx. In terms of protection and climate change, the extraction of carbon from industrial processes and the atmosphere itself has gained significant importance in the recent years. Carbon capture and storage, or direct air capture, are directly linked to adsorption-based processes and can be optimized using GeoDict. And that's what we're going to look at today. So, just some key facts about me. My name is Tabea Sterbak, and I'm an account manager in the filtration business area at Math to Market here in Germany. My educational background is chemistry. So during my master's, I worked with different kinds of zeolites and have also done a lot of adsorption measurements myself. So what are we going to learn today? As you can see here, we have a structure with multiple layers. So we look at the generation of a cabin air filter with 2 fiber layers and an active carbon layer. So we're going to model the layer geometries in GeoDict. As I said, we have 2 fiber layers, which we're going to model with FiberGeo. And we have an active carbon layer, which is kind of grains. So we're going to use GrainGeo. So as you notice, there's a geo at the end of the modules, which means those are structure generators. We also gonna look at the adsorption simulation. So we're gonna check what data you need to start such a simulation. And that's we're gonna do with our module AddiDict. So there's a dict at the end of the module name, which stands for prediction. And all our simulation tools end with dict. So as I said, we're gonna look at the data that you need to start such a simulation. We're gonna look at the setup, and we look at the results and see what you can gain from the simulation. But now, let's move to GeoDict. So this is our GeoDict user interface. When you go to the tabs here, we have, for example, a model tab or a prediction tab. So under model, you find our structure generators. Under predict, our simulation tools. In the beginning, we're gonna model our fiber layer. Therefore, we go to FiberGeo, and now you see here FiberGeo. We have some subtabs also. You could pile fibers or create fibers. In our case, we're gonna create fibers, so we choose create fibers and click edit. Here now we can choose our domain and type of the fibers. First, we choose our domain. So as our bottom fiber layer was a little bit longer in the set direction, we choose here 600 and leave everything as it is. We also leave the voxel length with 1 micron. So this is a voxel-based software, so 3D pixels. And in this case, we have microns, but you can also change here the scale. In our case, we don't want to have any fiber overlap, so we go with without. And as we want to have it a little bit less dense, we're going to choose 3 here in our object volume percentage. We move on to the next tab. You see here 2 different fibers. As we don't want to use infinite circular, we remove both of these fibers and choose a different fiber type down here. In our case, we want to use curved circular, and we click add, we click another add, and have 2 different ones here. First of all, we change the percentages to volume percentage. And then as we want to have this bottom layer, 2 different fibers, both half and half, we're going to choose 50% and 50%. So we have the same amount of them. Okay, so next we're going to go here and see, okay, we can change our diameter of the fiber and our length. First, we're going to change the diameter of our fiber. We click edit, and you can see here that right now there's a constant value, 10 microns. We want to choose Gaussian and then use here 4.5, a standard deviation of 1, and a distribution width of 2. You also have here a little forecast and can see if, your values make sense. Okay, so we click OK and then change the length of the fiber to 800 micron. In this case, you remember that our domain was 400 times 400 times 600. We just make sure here that the fibers don't end inside of the domain. And after that, we're going to change the orientation. Here we also click edit and we choose here 15, which means, as it says here, it is more oriented in the XY plane and less in the Z plane because we choose a higher value. And at anisotropy 2, we're going to choose 0.2, and we can check what it says. So a smaller value leads to the direction more oriented in the XZ plane. So we don't want to have it fully oriented in XY plane. Otherwise, we could have used in XY plane. All right, we click OK again and move on to the second fiber. Here we also change the diameter to Gaussian. In this case, we want to have a little bit thicker fiber, so we choose 8.5. We choose the same standard deviation and the same distribution width. Also have a forecast here, it looks good, click OK. The length, we're just going to go with the same, 800, and also choose the same values in the orientation, which was 15 and 0.2. Okay, now the fibers for the bottom layers are set, and we click OK. So normally I would click generate here now. As it takes a few minutes and I don't want to bore you, I prepared it beforehand. So I'm just gonna load the structure into the software with drag and drop, and you can see the two different fiber types. Okay, as we moving on to the grain, to the active carbon layer, we're first going to reassign the fibers so they have the same material ID. This just makes everything easier. So we go to Process Geo, we choose Reassign Materials and click Edit. So we want to go from ID 2 to ID 1, click OK. And just reassign, and now we have the same material ID for both fibers. Okay, before we move on to GrainGeo, we first need an empty space in the domain. So why is that? In GrainGeo, we want to use pile grains, so we want to let the grains fall onto the fibers. And for that, there needs to be an empty domain space. So we're going to go to Embed, click Edit, and then I just, put some domain space, click OK, click embed, and as you can see here, we have some space. Okay, I move on to, again, model, because it's a model generator. I click on GrainGeo, and also you have here multiple options, also a create grains, but as I said, we want to pile grains. We click on edit, and have here also the pile options. As we want to pile in the current domain, we'll click the checkbox, and we want to keep the fibers, so we want to keep the current objects, so we check the checkbox. All right, so what else are we looking at? You can here set your stopping criterion for the pile grains. In our case, we want to fill it to the rim, so we leave it at the default and move on to the object options. Here you see two different object types, one sphere and one box. We don't want both of them, so we remove both and we choose a different kind of type here. We're going to choose a convex polyhedron. We click Add. Same as with FiberGeo. You can just choose every structure, every type you want. Okay, so here you can see it looks already like a grain. But to make the grains like they are in the structure I showed you, it would also take a few minutes. So as we want to mostly focus on adsorption today, I also prepared those beforehand. So I'm going to just drag and drop the structure again. If you want to know exactly how everything works with the structure, you can always reach out and we can send you everything step by step. Okay, so now you can see here the structure. Maybe I'll change for you the colors. So, okay, so now you can see here the two fiber layers and the active carbon layer. I just created also the second layer just as we did before in FiberGeo, and then you can stack the layers together. So I just attached the second fiber layer on top of our active carbon layer. All right, before I now show you in GeoDict directly how the adsorption work, I want to talk shortly about how it is calculated with GeoDict. All right, so we have two different options, two different solvers in GeoDict. One is the tracer-based approach, and one is the field-based approach. As we recommend the tracer-based approach, that's what I'm going to tell you more about. So first of all, we're going to load a structure containing a porous material. That's exactly what we did. You can also, if you already have the product, if you already have a prototype and a micro CT scan, you can also just import the scans and then have your 3D model in the software. In the next step, you provide effective porous parameters such as porosity or diffusivity, and then GeoDict calculates a stationary flow field by solving Stokes or Navier-Stokes. In the next steps, first, GeoDict simulates the tracer movement. So we talk about tracers here. They carry a concentration, and as soon as they hit the surface of the porous material, they either lose concentration in the process of adsorption, or they gain concentration in the process of desorption. In the next step, we solve the equilibrium, and then we update the adsorbed load. So this is one batch, and we loop it over time batches. All right, so now we can move to GeoDict. As I said before, we need a prediction tool, which is AddiDict, our advective and diffusion transport solver or module. And here you can also choose other options, but we're going to go today for adsorption and click Edit. So I'm going to show you how to set up the experiment. And then we're also going to look at visualization and the results afterwards. Okay, so first let's set up the experiment. Here you can see the transport mechanisms that you can choose. So you can here choose to simulate diffusion or not. And on the right side here, you can choose the solver. As I said before, we have the tracer-based and the field-based. The tracer-based is the more simplified solver, and we recommend it right now as the performance is much better, but the field-based approach we currently improving, so the performance will also be better in the future, but both they give the same results. Okay, so here you can set the number of the batches that I talked about, and we have an approximate end time button. If you want to use that, you can do so, but you have to set everything of the experiment first, because the structure and what you choose in terms of the flow and the parameters will influence the value that you gain here. Okay, next we're going to move on to the flow boundary conditions. You have here an experiment input-output. You can choose, for example, mean velocity or the flow rate. We're going to go with mean velocity. And you can see here the flow direction is always set. So you need to make sure your structure is oriented the right way. Don't worry if you set up the structure and notice, oh, my axes are kind of wrong and it doesn't fit with the adsorption simulation. We have tools in the software where you can mirror your structure, rotate at a certain axis. So if you already modeled the structure, there's a way to change it. Okay, we're all set here. And we move on to consistent materials. Here you give the structure or the materials the effective parameters, such as porosity, in this case 50%, or permeability. Also, you can set here the temperature, if in case you want to simulate a higher temperature or lower temperature. Therefore, I have to say that if you have, for example, an exothermal reaction where the temperature changes during the adsorption, we can currently not simulate that. So a temperature change during the adsorption process is not possible with GeoDict, but as we want to move into that direction, we're already working on that. So in the future, we want to move into that direction. You can also set here the diffusion coefficient. And now we move on to maybe the most important subtab here, the adsorption. So here we have 3 different tabs: absorbate, adsorbent, and interaction. First, adsorbate. If you're not 100% sure, we have, as I showed before, some tooltips. You can just scroll over the words. But here we have a scheme. So the adsorbate is the carrier fluid. You can change the carrier fluid type here, either gas or liquid, and you can choose your concentration definition, molar fraction, concentration, or partial pressure. You can also set an absolute pressure if you want to change it, and here in our case, we choose the molar fraction of 400 ppm. Moving forward in the adsorption tab, here we choose our porous material. In this case, we chose material ID3, and as you can see here, you can only choose material ID3, so you can only choose the porous material. This is to prevent errors. What you can also do, as I talked about desorption before, you can here load an adsorbed load. So if you ran an adsorption simulation, you can just load here one time batch and then calculate back the desorption from there. Moving on to interaction, as I talked that we can do the desorption, it's important to say that we use a linear driving force model, so the rate constant for the adsorption and the desorption is the same. We currently also work on a dual driving force model, so where you can set different rate constants for adsorption and desorption, so we also want to have that in the future. All right, another important input that you need for adsorption in GeoDict is the isotherm model, or the adsorption isotherm. You can see here I chose Langmuir, but you can also choose freundlich, Toth, or you can also choose a table, just put in your concentration versus your load. And you have here a forecast of your isotherm and can check if the values make sense, if there's one value that is not really fitting, just to make sure. Okay, we also here have the isotherm equations, if you're unsure if your value is fitting. And as I talked about the rate constant, you can also set it here and also have the rate equation in case you want to check if you really have the right value. Talking about equations, in our simulation modules at the end, you can always find equations and references. So if you're interested in how do we simulate or which equations do we use, you can look at them here. And at the bottom, you also find references that you can look at. Okay. Now I would here click run. But as this is a simulation, so it would take a little bit longer. It would currently take 11 hours on just my normal work laptop. So you don't need a big cluster for it. You don't need a big work machine. You just take your normal work laptop. So I also prepared the simulation beforehand. So I'm just going to drag and drop the result. And this is how it looks. Okay, so here you get a report. First, we solved 41 batches, and the breakthrough occurred in the first time batch. 51.25% of the inflow concentration reached the outlet. So you can see here every time batch, the time and the outflow concentration, and also the total sorbate loading. To make it more visual, we also have plots. So the first plot is the isotherm, so your input parameter, and the second one is the breakthrough curve. So here you can see the breakthrough, and you can also use this to see how do parameters influence your breakthrough. So you can use GeoDict and then change porosity, flow, diffusivity, or also the grain size, and see how does the breakthrough curve change. You can also look at the total uptake and the layered data. So you can look at every time batch, and here's the set coordinate against the solute concentration. In the next step, we're gonna look at the data visualization. So here you also have every single time batch, and you can also load each of it, but you can also load the flow field or the trajectories. So we're gonna load a time batch in the middle. So we're gonna load 16th. You're gonna click OK, and this takes a little bit. Okay. So here you can see now the concentration, but we want to look at the loading. So we change it from concentration to loading here. Okay, now we want to see the loading only in our porous material. So we uncheck these buttons. And now we don't see any absorption or loading yet because the structure is laying over the volume fields. So we just uncheck the structure, and there it is. So now we can see, just a reminder, the flow came from here, so from the bottom. So we can see in the bottom, the grains are at full capacity in some regions, but if you go higher, you can see they're still green. So there's still capacity to absorb more. And by the time the simulation and the absorption moves on, all of the grains will be red. So of course you are also interested in how does it looks inside a grain. So we can clip the volume field and can look inside a grain. Can also go closer and see, okay, and here it is still inside green, but if we move more to the outside, we can see the effect that the outside adsorbs earlier, and as I said, as the adsorption moves on, also the inside will be at full capacity. Okay, so before we come to the end of our online seminar, I'm gonna show you also that we, as I said before, validated our adsorption tool. Here you can see a baked bed. We used Cocker et al. For this. This is CO2 on zeolite. We used 36 batches in this case with 500,000 tracers per batch. And as you can see, there's a great agreement between the experiment and GeoDict. What's important to say is also that we can use the adsorption also on the filter scale. So here you can see a single pleat with multi-layers, and the second layer is an active carbon layer. And of course, you also get the same results like the breakthrough curve or the adsorbed load. So what is the take-home message today? So with GeoDict, with the adsorption in GeoDict, you can get more insights into your dynamics, and you can understand the breakthrough times and the loading profiles better. You can use GeoDict to run a parameter study over the weekend and easily then see how the porosity, the flow, or even the grain size influences the breakthrough and what you can do to refine your product's performance. So you can use GeoDict to do digital prototype development, to cut material usage, to reduce testing time, but also get deeper product knowledge. As I said, you can see if an additional layer or a housing around the adsorptive layer, if some of this changes the adsorption behavior and how this influences the adsorbed load or the breakthrough times. So what are the next steps? You can either schedule a meeting directly with us and we can discuss your specific case and how the solution fits your specific application, or you can easily request a trial license. You can reach out and we get you started. And of course, we don't leave you alone doing this. So we're also going to help you. So now I'm at the end. Thank you for your attention. Also from my two colleagues, Christopher and Philip. I hope you got some good insights in how adsorption is done with GeoDict and how you benefit from it. If you have any questions, now is the time to write in our Q&A. Okay, so we have one question. It says, if the permeability value is not available, what is recommended for the simulation? First of all, we have also a tool in GeoDict where you can get or simulate the permeability value. So you can use GeoDict to get this value. And there's also a second question, can monolith adsorbent structures be represented? Yes, they can. Okay, there's another question. My question is, can we use this software for industrial applications like hydrogen purification, biogas purification using pressure swing adsorption? This is a really specific question. In this case, we would have to check first. We can reach out and we can see what data you have, what's exactly the setup, and then I'm sure we can find a solution for that. Another question is, what coal adsorbent parameters are readily available in GeoDict and what parameters are not? So we have a material database. So I'm not sure if I understand the question correctly. So we have a material database where you can choose your material from. In terms of adsorption, you choose just a porous material, so just as manual, and then you give parameters to the material, like permeability and porosity. So you have to set the parameters. Okay, the question is, in the example, what do the fibers represent? Are they an inert material used to distribute the fluid? So this is just an example case. This can either be fibers they are before the adsorptive layer to capture particles, or just as a protection layer for the adsorptive layer. So this is just as an example to what the software can do. So there was a question in the beginning that I've missed. It says, do you have a correlation between your simulation results with test data, particle captures? Oh, yeah. So I only showed absorption, but we can also do particle simulation. Lifetime, filter lifetime, or filter efficiency, where you can see the filter cake and the depth filtration. This is no problem. Yeah. There was a question for multi-component liquid mixtures. So right now, it was also answered in the chat. It's only possible to simulate a single component, but we're working towards the multi-species applications. There's one more question. Is it possible to evaluate the best fit adsorption law and parameters by improving geometry, fluid and solid material parameters? I'm not sure what you mean by adsorption law, but if you wanna do like a parameter study or find the best parameters for your material or your setup, this is possible. So it is meant to help improving your process and your product. I was wondering how you model particle transport in the porous media. Specifically, which governing laws of force balances do you consider for particle motion, and whether interparticle or particle surface interactions such as van der Waals forces, Hammaker constant, are included in your model? So I think it's easier to explain that in a separate email or meeting, but as a shortcut, yes, we can model the particle transport. So we have a module that's called FiberGeo, where you focus on particle simulations like cake filtration, depth filtration. We also have, for example, the Hammaker constant that you can put into the simulation. So it's included in the model. But yeah, I think we can, it's easily if you're reaching out to us using our email, and then we can also give you some, slides, some papers to it, so you have the full knowledge of how and what we're doing. All right. As there are now no more questions, I want to thank you again for joining for this online seminar, and I hope you enjoyed it. And as I said before, feel free to reach out using our email or using the QR code to book an online session. We would be happy to look at your specific application and help you, make it work with GeoDict. Thank you, and have a good day.